Okay, gravitation is something that we have already been introduced to, but haven't really dived into deeply. We know g, of course, little g for the Earth is 10 meters per second squared, but this has real limitations here because it only really involves the surface of the planet. It only involves the Earth. We can figure out the acceleration due to gravity at a greater distance away from the Earth, and we don't actually know what it really is for other planets without a direct comparison of the Earth. So let's figure out where this comes from. Now, you end up getting a formula like in my notes. I say that the acceleration due to gravity is g is equal to big G m over r squared. This g is a constant. It's 6.67 times 10 to the negative 11. Okay, very, very small constant. This mass is the mass that you're trying to find the acceleration due to gravity of. In other words, it's usually the planet or the sun. It's not the satellite, it's not the object you're placing in that field like a person or a book. I generally will write CB for center body just to differentiate that, so you know that this is the mass that we're actually in orbit around. And of course, because we're going to be talking about circular orbits, I'm using r, the distance from the center, instead of d, because it's generally a radius. Just so I can show you this, if this is 6.67 times 10 to the negative 11, and the mass of the Earth, the mass of the Earth is actually 5.98 times 10 to the 24 kilograms, and the radius, the distance from the center to the surface of the planet, would be around 6 times 10 to the 6 meters. It turns out if I plug in these numbers into here, I'll get approximately a value of around 10 meters per second squared. So that's where this comes from for the Earth. Again, I can stick in any numbers knowing that I have a constant, the distance away from the planet, and knowing the mass of the planet, I can figure out its acceleration due to gravity at any given moment. Knowing this formula here, we already knew a formula that was Fg is equal to mg. Okay, Fg is equal to mg. A lot of students get confused about, well, which mass is this? This mass is what I'm actually putting into the gravitational field. So this would be the satellite, the book, the pencil, possibly another planet that's getting affected by this gravitational field. Now if I expand this a little further from what we already knew, the actual equation is Fg is equal to g, I'm going to say m1, m2 over r squared. This m1 could be the center body. In other words, right here, if you look at this part right here, this is g, and this is m times g. Okay, this is the mass I'm putting into it. Here's the acceleration due to gravity caused by that other object. So just so you can distinguish between the two here, again, this will give me newtons, this will give me meters per second squared. One last thing I want to show you here is, based on this formula here, is that if generally a satellite, okay, if here's a planet or a star or whatever you have here, a satellite is anything that orbits. So in fact, the moon is a satellite for the Earth, and the Earth is a satellite for the sun. A satellite doesn't have to be a metallic object that sends out TV or radio waves or anything like that. It'll essentially is anything that's orbiting. Okay, well, because it's orbiting, it has a radius r away from the center of the Earth or the center of the planet. It's going to have a little mass, and so will this have a mass as well. I'm going to call that CB. And in fact, if I want to figure out, well, the force of gravity acting on this object will only be your force of gravity. There are no other forces acting on it. You'll notice that it's pulling it always towards the center. Okay, I want you to be aware of that it's always pulling towards the center. And so in fact, this will be my net force. And I'm going to just say, well, then that's g m1 m2 over r squared, but that's going to be equal to my net force, which is ma. Instead of writing a, I know that this is moving in a circular pattern, so I can write v squared over r. You'll notice I can get some cancellations. That's gone, this is gone, one of the masses is gone, and again, to remind you, this is the mass right here. Okay, so what I'm left with is the gm of the center body divided by r, which equals v squared. And hence, v is going to be equal to the square root of g m center body all over r. This is the speed of a satellite. Okay, so it's the speed of a satellite going around a planet or a star, what have you. Again, it's only dependent on the mass of what it's going around and the distance it's away. Okay, and this will be the automatic speed of that. Now, and so this formula is very, very useful in terms of calculating things. Just keep in mind here that v could also be equal to 2 pi r over the period. And this is just basically just to remind you, v equals d over t from circular motion. Keep these things in mind because sometimes it's useful, instead of figuring out what v is, to figure out what the period is. And if you know r, you could substitute and actually find that as well.